Hi, I'm José Alvarez, Engineer and Director for Video Technology at Xilinx. Today we'd like to talk to you about image formats and various ways of representing images. Let's first start talking about the sensitivity of the human eye to color primaries. You could represent any image in 3 color primaries, and the sensitivity of the human eye is not equal to each of those primaries. In this color matching function diagram, you could see the response of the human eye to the green, the red, and the blue components of a primary. Here, for instance, you could see very easily that it requires a lot more power to represent blue colors than it takes to represent green or red. This will be very important when we talk later about image representation and especially subsampling of images. First, let's talk about common ways of representing images. One common way of representing images is as a two-dimensional array of pixels. In this graph, you could see that you have sets of rows of pixels and columns. You could also call them lines and pixels individually as well. In this example, each pixel is represented by an RGB triplet that follows the color primaries that we talked previously. These pixels are what are called co-located, meaning that the R, G, and B components corresponds to one physical location of the picture itself. It is possible to represent images using 3 color primaries. You could use more, and in many cases today, 4 primaries are used. But essentially, 3 color primaries are sufficient to represent every image. A very common one used in the color matching functions that I showed earlier is the RGB domain. And we've seen the response of the human eye to those 3 different spectral densities in the red, the green, and the blue domain. That image representation format is very good for displays or printing in other areas where you need to present an image. But for processing images, the RGB domain may not always be very appropriate, and that has to do with the way that our eyes work. So, it turns out that our human eye is less sensitive to changes in color than changes in luminance. And so therefore, taking the human visual system into account, it's easier to see that it's possible to represent the 3 primary colors instead of RGB into a luminance component. It's not a color, but just a component that denotes the brightness and contrast of images, and another 2 components that denote the color. In this case is a color difference signal when you talk about YCRCB. CRCB being a color difference in the red, meaning color difference from the luminance, and the blue, a color difference for blue from the luminance. In a way, in a formula, it would be R minus Y and B minus Y. And so it's a color difference signal that allows you to represent with 3 color primaries the whole spectrum of images. We're not going to get into topics that have to relate to gamut, which is the color range, or other things, but we will concentrate today in the various color models that can be used. For example, perceptual models are many, based on the same principle of the human eye. And they could be the YCRCB, which is used very common in video systems, the CMY, which represents cyan, magenta, and yellow. The yellow color in this case is a representation of luminance because it's close to the luminance response. HSL, hue, saturation, and lightness. Lightness being, again, similar to luminance, and hue and saturation denotes colors and how intense they are. And so HSV is similarly another format that is a perceptual, as well as LAB, L being luminance and AB are just other 2 components. This graph is not complete, but just meant to indicate the various color models that can be representing with the principle of 3 color primaries. And we will see later how it's important to treat those color models, especially when you want to either transmit, store, or process images. As you may recall from the color matching functions graphs that we showed earlier, the response of the human eye to different color primaries is not the same. we are a lot more sensitive to the green spectrum than we are from the blue spectrum. And there's even a little bit of the red spectrum that spills into the blue. Well, we can do, because of the response of the human eye, we could do color subsampling. In other words, we could use less samples to represent color than we use to represent luminance, the Y component. This graph shows that there are many subsampling alternatives that you may approach. For instance, in the RGB domain, you could very easily represent your tri-stimulus primaries in an orthogonal way, where every pixel has R, G, and B components in every line and every pixel and every column as well. Another common way of representing the RGB domain subsampling is Bayer subsampling. Here, I've represented Bayer subsampling, where you may be able to appreciate that there's twice as many green components as there are red and blue. Again, related to the fact that our eyes are less sensitive to the red and green spectral components of images. That's a typical Bayer subsampling. But there are other more human perceptual models that we can subsample, one of them being the YCRCB. YCRCB can be used generally to represent luminance and color difference in signals, but there are other related formats that are similar to it. For instance, YUV or YPRPB. So for the purposes of this discussion, I'm going to use YCRCB and YUV interchangeably, though they're not the same. So in this case, representing the subsampling by a 4:4:4 ratio, meaning the luminance and chrominance blue and chrominance red components are sampling at the same rate. So you will have three components, CB, Y, and CR, CB, Y, and CR for every pixel in the line and every line. Another way of subsampling the chroma is in the 4:2:2 format, in which you could see here that every other pixel has chroma and every other pixel has no chrominance components, just the luminance, and all the lines are the same. One very common format as well to represent images is the 4:2:0 format. A lot of compression schemes use the 4:2:0 format, and that's essentially going subsampling not only in the horizontal domain, but also in the vertical domain. In this case, you subsample every other pixel in the horizontal domain and every other line. You can see here that this line here has chrominance components that are subsampled, and this line here has no chrominance at all, and so on and so forth for the entire two-dimensional image representation. So you could see here that there are different colors of sampling schemes that follow the response of the human eye. They could be done in any of the color spaces, whether RGB or YUV. Continuing with the color subsampling theme, in this graphs I have represented the YUV sampling domain in a different way for easier explanation. And here, the YUV 4:4:4 domain, I've represented X's for the luminance components and circles for the chrominance components. So it's easy to see here that in this two-dimensional array, you have as many luminance components as you have chrominance components, and therefore the 4:4:4 sampling substructure. In the 4:2:2 domain, it's very easy to see that you have half the chrominance components in the horizontal domain, but every line has chrominance itself. And then finally, in the 4:2:0 domain, you could see that every other pixel has chrominance and every other line has chrominance as well. Following the discussion of color subsampling, in computer vision, images are generally stored in files, in a file system. To represent the nature of the file, a 4cc code has been used for quite a long time, and 4cc stands for 4-character code. This 4-character code it's a convention used to indicate what type of data is stored in a file, and 4cc codes apply to RGB images as well as YCRCB, YUV images. But for the sake of this discussion, I will only talk about the luminance and chrominance formats. Not all of them, but some typical ones. So for the YUV422 subsampling, for instance, there are two very common 4cc codes that are used. One of them is the so-called UYVY code, which essentially indicates the exact subsampling of the chrominance components, where the U and V components belong to a Y, and there's a Y without any other chrominance. So it's exactly as it says here. One Y has two chrominance components, the other Y has none. This 4cc code, to me, makes a lot of sense. There are other codes that are not necessarily so obvious, but in reality, they represent the same image information. For instance, YUY2, for 2 meaning a factor of 2 subsampling in the horizontal direction. It's only 4 codes, so therefore there are only 4 letters used here, but essentially this will be equivalent to this. There are other ways there are other 4cc codes that represent the image, but they represent perhaps byte ordering changes in little endian or big endian machines. Similarly, for the 420 subsampling, common codes used are YV12 or I420 or IYUV. Again, there's no specific way to know which file format will be used, but these are very commonly used by many companies to represent this subsampling. So whenever you see any of these 4cc codes, you know that they relate directly to this subsampling. Another factor to consider in representing images is image sample ordering. So the ordering of the pixels, the triplets in many cases, has a different way of being expressed. For instance, there are 2 generic ways that one could represent that ordering. One of them is pixel order or display order, where you have triplets. In this case, I've chosen to use CB, Y, and CR for every component. In this case, it would be the 444 sampling that you saw previously. So for every pixel, you represent the triplets. In memory, these components will be stored, for instance, like this. If each one of these boxes is a location of memory, and this is the lowest memory, you go from low to high memory, and then you see the components stored. In this case, let's assume that each component is 8 bits. So it's 1 byte per component, CB, Y, R, CR, CB, Y, CR, and so on and so forth. Another way of representing is in what is called the planar ordering, in which case all of the luminance components are represented together, and then the chrominance components, either the CB, CR, or CB, depending. The memory organization would look like this, where this is the lowest memory, highest memory, so it is increasing memory locations. All of the luminance components are stored consecutively, as such, and then the blue and the red components. We just saw that there are generally 2 ways of storing pixel data in triplets in memory, either in display or pixel order or in planar order. Either way, eventually you have to face on how to store the actual data, pixel data, in memory. And so the memory organization is a very important consideration for your processing, especially when you're trying to maximize memory bandwidth. In this graph, I've represented the first 2 generic ways of storing memory. One which is called big endian, and many computers, microprocessors, use big endian storage memory organization, or little endian. In big endian, your starting memory is your MSB, your most significant byte in this case, in a 32-bit word. So you start with your MSB, and as memory increases, you go into your LSB. This is how we write numbers, from the most significant to the least significant. The other way of storing in general is what's called little endian. In that case, you start in your memory location from low memory location to high memory location, and then you start with your LSB, and then you move to your MSB. Another way of storing that data, and now you have to make a decision. You have RGB triplets, for instance, and You can store them in little endian or big endian way, but how do you do it? You may do it in the packed mode, in which case you start to store RGB, and immediately you start with RGB and so on and so forth, assuming that you're storing 32-bit words, which is a very common today way of storing pixel data in physical memory. And then you go on. This is a very efficient way to pack the memory. It may not be so efficient if you want to read this data in a computer program, because then you would need to separate the components individually. But nevertheless, it's very efficient for hardware implementations and very fast. Another way that is practical, though a bit wasteful, is to store it in word-oriented formats, where you decide to store the RGB components lined up into 32-bit word starts here. So RGB and then nothing, RGB and then nothing. In formats, which I haven't talked to today, that use an alpha component, an extra component to indicate blending, then this will be the perfect location for storing alpha. But for RGB components, typically this is the storage, whether RGB starting with the most significant bit or starting with the least significant bit, depending on what the memory organization is. Let's review what we've seen up to this point. We've seen that there are multiple color representations, that there are various ways of subsampling that image information in either the horizontal or the vertical domain. We've seen that there are a variety of color formats in which you can represent images. And not only that, but you have the option of ordering words or bytes in different ways, either big endian, little endian, packed, or word ordered, and obviously different memory organizations. In the next graphs, we will see how you can use FPGAs to your advantage to represent all these image color formats in very efficient ways. So far, we've seen that there are many ways of representing images, color formats, byte ordering, etc. And the reality is that as a computer vision implementer, you can never really rely on getting the image format that you expect. Many times, your images are formatted in one domain, and you by necessity need to convert to another domain that is related to either your processing or even your display. And so in those situations, you can appreciate that having a very flexible way of converting from one format to the other quickly becomes very important. And this is where FPGAs are a perfect solution for those problems. Xilinx provides a portfolio of cores that are geared exactly to solve this problem. In the next two graphs, we will see some of the IP cores that are available. Let's start with what we call a color space converter. A color space converter performs a very fundamental function. Let's assume that you are processing your computer vision algorithm in the YCRCB domain, and we have seen that that's a very good domain to represent images in the way that the human visual system works, with luminance and chrominance difference components. And you get input that comes perhaps from a camera, perhaps from other device that outputs RGB domain. So very quickly you can convert in real time from the RGB domain to the YCRDB domain, process your data, and on the output display it on a display back into the RGB domain using another IP core that makes your job very easily and convenient. Another typical problem to solve is called color correction, in which you have an RGB component that needs to be color corrected. This is very common in imaging applications. Your task is to convert using a matrix that is called the CFA, the color correction, the CCM rather, the color correction matrix from one domain to another one, process in the converted domain, and perhaps even at the end use a coupler IC to convert from little endian to big endian or to any other format, as you could see here. In this case, you convert from the RGB domain to a domain that has the LSB, the green component, that may be more closely related to the luminance, and then the B and the R components, completely in any way that you require. Yet another way of using Xilinx IP is to perform what is called gamma correction. We're not going to go into the details of what gamma correction is here, but suffice it to say that in addition to our human visual system to be sensitive to frequencies and ranges, we're also are very sensitive to dynamic range. Gamma correction is an operation that can resemble the response of the human eye. So for instance, in a display, instead of displaying RGB information linearly, it can be displayed non-linearly to approach the sensitivity of the human eye and match it to computer monitors. Following our discussion of why FPGAs are an excellent solution for processing image in various formats, let's continue with examining some of the video IP cores that Xilinx has in its portfolio. There's a color filter array interpolation core that essentially converts RGB data subsampled in the Bayer domain to RGB triplets. There's also a chroma resampler. A chroma resampler is a very interesting and useful IP because it allows you to process data in a full sample domain, 444, and yet get the data in a subsample domain. In this example, I have represented YCRCB data in the 422 domain, that it's upconverted into the 444 processing domain. After processing is done, it's converted perhaps to something else. For instance, the 420 domain for transmission or storage in one of those formats that are key for processing in a compression device, for instance in 420 domain. In this case, either way, this example is just one of many where you could go from either one of the domains to another one. For instance, from 424 to 422 or 420 or vice versa. This shows the range of flexibility that you are allowed because of these choice of IP that is already done for you to address all of these different color formats. Today we have very briefly touched upon various image color formats, subsampling, ways of storage image information in memory, and transmitting. We've looked at various ways of representing the image data according to the human visual system, both in the RGB and the perceptual domains, for instance, YCRCB. We've seen how important it is to be flexible in dealing with various image formatting domains, and how the flexibility that provided by FPGA comes in very handy when you want to implement your system. Not only that, there's a whole set of IP cores that are part of the Xilinx catalog that will allow you to very quickly and easily convert from one domain to another depending on your application. For more information, go to www.xilinx.com and search for video IP cores to see the full line of IP cores provided by Xilinx. Thank you for your attention.